So see the question number 36. Block of mass 4 kg is suspended through two light spring balances A and B. Then A and B will read respectively. She mentioned that the spring balances are light. That means you have to assume that mass of each spring balance is negligible compared to the mass of the block. As I discussed earlier in the beginning of connecting bodies, that when a block is suspended by a string whose mass is negligible compared to the mass of the block, the magnitude of tension will be the same at all cross sections of the string. So here mass of each spring balance is negligible compared to the mass of block. Therefore, magnitude of the tensional force, which we of course call it as elastic force in the spring, that will be same in both the springs. And for the block to be in equilibrium, the magnitude of the tension force on the block or magnitude of the elastic force on the block by the spring B must be equal to the weight of the block. So magnitude of tension each spring must be same, that will be equal to the 4 kg weight. Therefore, both the springs will read 4 kg weight. Therefore, for question number 36, third option is the answer. See the question number 37. In the figure, if the surface are frictionless, the ratio of tensions T1 and T2 is. So here, all the blocks, if you assume that the strings are inexchangeable, the blocks move towards right. All the three blocks move towards right, the same magnitude of acceleration. I do not buy A. So to find T1, you can consider the two blocks of masses 3 kg and 12 kg, and also the string connecting the two blocks, all these three, as one system of mass 3 plus 12 or 15 kg. So when you consider the two masses 3 kg, 12 kg and the string between the two masses as one system, then T2 will become an internal force which should not be considered for application of Newton's second law. When you consider two or more number of objects as one system, then the force exerted by one object in the system on another object in the same system is called the internal force. The internal force do not enter into the equation for Newton's second law. So if you consider the two masses 3 kg and 12 kg and the string between the two masses, all these three as one system, then the external force on the system in the horizontal direction is T1. So unbalanced force on this system of the two masses 3 kg, 12 kg and the string between the two masses is equal to T1. So this T1 you can write 3 kg mass of the system into acceleration, 3 plus 12 kg into magnitude of acceleration. So to find T2, we can apply Newton's second law for 3 kg mass separately. So only unbalanced force acting on the 3 kg mass in the horizontal direction, the tension T2. That means if you consider a single block of mass 3 kg as one system, then the resultant force on this system in the horizontal direction T2. That is equal to product of mass of system into acceleration. Acceleration is same here for all the three blocks. So if you divide T1 with T2, 3 plus 12 by 3, A gets cancelled. So that is 15 by 3 or 5 by 1 or 5:1 is the answer. That is the easier way you can do it. Otherwise, you can also solve the problem by alternate method. That is by applying Newton's second law for each mass separately. So the tension force T2 on 3 kg mass acts along the string and away from 3 kg mass. The tension force exerted on the 12 kg mass by the same string acts along the 12 kg mass and away from the string. Call suppose these three blocks as the M1, M2, M3. Of course, we assume that the mass of each string to be negligible compared to the masses of the blocks at the two ends of each string. Therefore, magnitude of this tension at the right end of the string will be can be assumed to same as magnitude of tension at the other end of the same string. So, tension force exerted on M2 by the first string on its right side acts along the first string and away from M2. The tension force exerted on M1 by the first string acts along the first string and away from M1. So this T1 here is the tension force on M1 by the first string which acts along the first string and away from M1. Here T1 is the tension force on M2 by the same string which acts along the string and away from M2. Because mass of the string is negligible compared to the mass of M1 and M2, magnitude of tension will be same at both ends of the string. You can resolve this F into components. The horizontal component will have, if we can resolve two rectangular components along horizontal and vertical direction. The vertical component will F sine 30 degrees. So magnitude all the three blocks are moving horizontally. There is no motion in the vertical direction. So by vertical component of the resultant force on each mass is 0. So resultant force on each mass will be equal to resultant of forces in the horizontal direction. So I am talking about the alternate method for same question. That means we are analyzing it completely. Resultant force on M1 is equal to F cos 30 degrees minus T1. That is equal to mass M1 into acceleration. Now for the mass M2, T1 acts towards right, T2 acts towards left. So magnitude of the resultant force on M2 towards right. T1 minus T2. That is equal to M2 into A. For the mass M3, T2 acts towards right. So resultant force on M3 has magnitude T3. That is equal to M3A. If you add all the three equations, this is not T3, this should be written T2 only. Resultant force on M3 is equal to T2 in magnitude, which acts towards right side. This must be corrected. So if you add all the three equations, minus T1 plus T1 minus T2 plus T2 gets cancelled. You get F cos 30 degrees equal to M1 plus M2 plus M3. You can as well write this equation directly if you apply Newton's second law for system of all the three blocks and the two strings between the blocks. So you get common accelerator of each block if you are given the value of F also in the problem. After calculating F, you can find T2. If case numerical value of F is given, you can find T2 by substituting A in the last equation. If you add these two equations, you get T1 equal to M2 plus M3 into A. Like that. You can complete the calculation yourself, even by the alternate method. For question number 37, fourth option is the answer. See the question number 38. This is a more easier problem. Player caught a cricket ball of mass 150 grams. So let us denote the mass by m. Here 150 grams, we can write 150 into 10 power minus 3 kg. Moving at the rate of 20 meter per second. So initial velocity of the ball is 20 meter per second. The catching process completed in 0.1 second. That means in a time interval of 0.1 seconds, the velocity of the ball becomes 0. The force of blow exerted by the ball on the hand of the player is equal to. So average acceleration of the ball during the catching process. Is equal to V minus U by T. We are giving positive direction for initial loss of the ball here. So you get A equal to minus 200 meter per second square. From Newton's second law, so average force exerted on the ball, of course by the hand, is equal to mass of the ball into average acceleration. That is 150 into 10 power minus 3 kg into minus 200 meter per second. You get minus 30 newtons. The negative sign indicates that the average force acting on the ball during the motion is opposite to its initial velocity. So the force exerted on the ball by the hand of the person has average value of 30 newtons. So from Newton's third action, reaction force are always same in magnitude. So magnitude of the force exerted on the hand of the player by the ball will be equal in magnitude and opposite in direction to the force on the ball by the hand. The force on the ball by the hand is minus 30. So mathematically you can write it as 30. That means the positive sign indicates that the force on the hand by the ball is in the direction of the initial velocity of the ball. So for the question, answer is 30 newtons. So for 38, question number 38, third option is answer. See the question number 39, this needs no calculation. There is one result which we have discussed in the vectors, triangle law, based on the triangle law of addition of vectors. The conclusion I have discussed in the past based on the triangle law of addition of vectors is that in general, if three vectors can be graphically represented along the three sides of a triangle, all taken in the same order, then the magnitude of their vector sum or resultant is 0. In this case, it is given that the three forces start acting simultaneously on a particle which is originally moving with velocity v bar. The first force acts along AB. The second force acts along BC. And the third force acts along CA. So the three forces are represented graphically along the three sides of a triangle, all taken same order. Therefore, magnitude of the resultant of three forces is 0. So when net external force on the body is 0, from Newton's first law, if net external force on the body is 0, the body will either remain at rest or move with uniform velocity. The body is originally moving with velocity v bar before application of these three forces. Then even after application of three forces, it continues to move with the same velocity v bar in the same direction because the resultant of the three forces is 0. So fourth option will be the answer. Look at the question number 40. One end of a massless rope which passes over a massless and frictionless pulley P is tied to a hook C, while the other end is free. The maximum tension that the rope can bear is 720 Newton. What value of maximum safe acceleration can a mass of 60 kg climb on the rope? So here the man is just shown in the form of a block of mass here, 60 kg on the right side. Of course, the diagram, this block does not look like a man, but still, in the language of physics, we treat it the man also like a body of mass 60 kg here. So the man pulls the string vertically downwards. The man pulls the string vertically downwards. So the man pulls the string vertically downwards. So force exerted on string by the man acts vertically downwards. According to Newton's third law, to every reaction there is always an equal and opposite reaction. A reaction is the force exerted on string by the man which acts vertically downwards. So the direction of the reaction will be opposite to action. If action is the force on string by the man, reaction will be the force exerted on man by the string. Action, reaction, force are always equal in magnitude but opposite in direction. So if the force on string by the man is directed downward, the reaction force on man by the string will be directed upwards. Both will have same magnitude, denoted by capital T. But when we draw the free body diagram for the man, in the free body diagram for the man, we must show only the forces which are acting on the man. Should not indicate the forces exerted by the man. So this would not be shown in the free body diagram for the man. This must be shown in the free body diagram for man. So the weight mg acts downwards of the man, which is the gravitational force of man by the earth. The tension force by the string, I mean this reaction force on the man by the string, acts upwards. Only two forces act on the man here in the vertical direction. So magnitude of the resultant force of the man in the upward direction can write T minus mg. From Newton's second law, that is equal to mass into acceleration. So maximum acceleration with which a man can move up is equal to magnitude of the maximum value of the tension, which is a string can or rope can withstand, minus magnitude of his weight to the man by m. Maximum tension it can withstand is given as 720 Newton. Mass of the man is 60 kg. Take G as 10 meter per second square. Come on, copy down the working if you want to copy down the working. You can get the answer as 2 meter per second square. So for question number 40, first option is answer. See the question number 41. A string of negligible mass is going over a clamped pulley of mass small m. Suppose a block of mass capital M, as shown in the figure. The force on the pulley by the clamp is given by. Let us consider the force acting on the block here. The mass of block is denoted by capital M. The first force which acts on the block is its weight mg, which is the gravitational force of the block by the earth. Then the second force on the block is the tension force. by the string. The tension force by the string on the block acts along the string and away from the block, acts upwards. So magnitude of the resultant force on the block in the upward direction equal to T minus mg. But the block is in equilibrium, so this must be 0. So magnitude of tension in the string equal to capital M into G. Let us consider the force acting on the pulley. There is a one tension force by the horizontal path of the string on the pulley, which acts along the string and away from the pulley. The mass of the string is negligible compared to the masses of the block and the pulley. Then magnitude of the tension will be same throughout the string. There will be another tension force exerted on the pulley in the vertical direction, which acts along the vertical path of the string and away from the pulley. The weight of the pulley will be equal to small m into, has magnitude small m into g, which acts vertically downwards. So when the pulley is also in equilibrium here, so net force on the pulley must be 0. I have shown only 3 forces on the pulley here, 1, 2, 3 here. So magnitude there is another force on the pulley by the clamp. And the resultant of all the force acting on the pulley is 0. The force exerted on the pulley by the clamp must be opposite in direction, but equal in magnitude to the resultant of these 3 forces. So here, let us suppose V is the vertical component of the force exerted on the pulley by the clamp, and let H denote the horizontal component of the force exerted on the pulley by the clamp. Again repeat, V is the magnitude vertical component of the force exerted on the pulley by the clamp, which must be directed upwards because to balance these 2 forces in the downward direction. H denote the magnitude of the horizontal component of the force on the pulley by the clamp, which act towards right to balance this T. So for the pulley here, the horizontal component of the resultant force can write H minus T, that must be 0, or horizontal component of the force on the pulley by the clamp has magnitude T or equal to mg. So vertical y component of the resultant force on the pulley in the vertical direction called V minus mg plus T. That should also be 0 because the system is in equilibrium. So magnitude of the vertical component of the force on the pulley by the clamp is equal to mg, small mg plus capital T. Capital T equal to capital M into small g. So magnitude of the vertical component of the force exerted on the pulley by the clamp. So magnitude of the actual force exerted on the pulley by the clamp can be written as root of h square plus v square. Can substitute h equal to capital M into small g, V equal to capital M plus small m into G. So within the root you can take G square common. Under root of G square you can write G. If you want to copy down the solution of the problem, come on. Copy down the solution of the problem. You can take a pause and copy down the solution of the problem. So for question number 41, fourth option is the answer. So look at the question number 42. Two particles of mass small m each are tied at the ends of a light string of length 2a. The whole system is kept on a frictionless horizontal surface with a string held tight so that each mass is at a distance small a from center P, as shown in the figure. Now the midpoint of the string is pulled vertically upwards with a small but constant force F. As a result, the particles move towards each other on the surface. The magnitude of accelerator of each particle when the separation between them becomes 2x is. So the two particles lie on the smooth horizontal plane here. So the force is applied in the vertical upward direction. The initial separation between the two particles is A plus A to A. You have to find magnitude of accelerator of each particle when the separation between them becomes 2x. Come on, look at the solution of this problem. So here in the diagram at the top on the left side, I have considered the force acting at this point, middle point of the string. I have considered the force acting at the middle point of the string at the instant when each half length of string makes an angle theta with the initial position of the string. So at the point O, or we can say on the particle at the point, middle point of string, there will be two tensile forces, each of same magnitude T, which act along the string and away from that point O. So each tensile force can resolve into rectangular components in the horizontal and vertical directions. The component T cos theta acts horizontally. The component T sin theta acts vertically downwards. So the two horizontal components of the two tensile forces acting on the point O are equal in magnitude but opposite in direction, so they cancel out. The vertical components of the two tensile forces have same magnitude each equal to sin theta, act vertically downwards. So net force acting at the point O in the vertical direction can write F minus 2t sin theta. We assume mass of string to be negligibly small compared to mass of each particle. Therefore, this can be net force equal mass and acceleration. This mass can be taken as 0. So you can write F equal to 2t sin theta, or magnitude of the tension in each part of the string will be F by 2 sin theta. In the other diagram at the bottom, I have shown the free body diagram for one of the particles connected to the one of the ends of the string. So the tension force on the particle by the string acts along the string and away from the particle, which you can resolve into rectangular components along the horizontal and vertical directions. The horizontal component of the tension with magnitude T cos theta acts towards the other particle. The vertical component of the tension with magnitude T sin theta acts vertically upwards. The weight mg also acts vertically downwards here in the vertical direction. Normal reaction force acts vertically upwards. Here it is from the description of the problem. You can assume that the two particles move only on the smooth horizontal surface. They have no motion in the vertical direction. So magna the resultant force acting on one of the particles in the horizontal direction or along x-axis is equal to t cos theta. So magna the x component of the acceleration of each particle is equal to magna the x component of the net force on each particle by mass of the particle. You can substitute t equal to f by 2 sine theta. So magna the acceleration of each particle can be written as f by 2m tan theta or f cot theta by 2m. So on the figure, tan theta is equal to opposite side by adjacent side. So length separation between the two particles is 2x. I mean, you are asked to find magnitude of acceleration of each particle at the instant when the separation between the two particles becomes 2x. So horizontal distance of each particle from the midpoint of the string is x. Length of each part of string is a. So this length of this part from Pythagoras theorem is root of a square minus x square. So tan theta is equal to opposite side by adjacent side. So we can write tan theta equal to root of a square minus x square by x. So magnitude of acceleration of each particle will be equal to f by 2m into x by root of a square minus x square. This problem is given in 2007 in IIT-JEE exam paper, but I observed this problem in the past in the world edition of Resnick and Halliday, second edition of Resnick and Halliday, where you are asked in the question given in Resnick and Halliday, you are asked to find magnitude of the relative acceleration between the two particles. Of course, for the question I have shown on the screen, this is the answer. If you want to copy down the working, you can copy down. So, you magnitude of acceleration of each particle towards the other particle, but the accelerations of the two particles are directed towards each other. Means directions of the acceleration of the two particles are opposite. So, magnitude of the relative acceleration of one particle with respect to the other particle, or magnitude of relative acceleration of approach, the sum of the magnitudes of accelerations of the two particles. Magnitude of acceleration of each particle is same. So that is 2 times the magnitude of acceleration of each particle. So that comes out f into x by m into root of a square minus x square. In case that is asked. Of course, for the question you are not asked this relative acceleration. Those who want to copy down the solution of the problem can take a pause and copy down the solution of the problem. So for question number 42, which I have just discussed now, second option will be the answer. So look at the question number 43. Two blocks A and B of masses 2m and m respectively are connected by a massless and inextensible string. The whole system is suspended by a massless spring as shown in the figure. The magnitude of acceleration of A and B immediately after the string is cut are respectively. So initially the system is in equilibrium. That means in the first case, if you consider the two blocks A and B and the string between the two blocks, all the three as one system of mass 3m. Then for the system of the mass 3m, in the original arrangement, the weight of the system acts downwards, the elastic force by spring acts upwards. Let F subscript S denote the magnitude of the elastic force by the spring. that will proportional to the elongation of spring. Later in the next chapter, later work power energy will discuss that. This can be done K times the elongation of spring from its natural length, where K is the elastic force constant of spring. So originally the system is in equilibrium. So magnitude of the elastic force by the spring is equal to 3 mg. That means here I have shown the free body diagram for the system of the two blocks A and B along with the string between the two blocks. When you consider two blocks A and B and the string between the two blocks as one system, the tensional force in this string will become an internal force. So that's why it's not shown in the figure. So when the string between the two blocks A and B is cut, so if we analyze the situation, just after string between A and B is cut, at the instant just after the string between A and B is cut, the free body diagram for the block A can be written as equal to 2mg downwards, its weight of the block A. The elastic force by spring acts upwards. At the instant just after the string between the two blocks A and B is cut, but the spring is not cut here. So the magnitude of the elastic force by the spring on the block A will be same, because elongation of spring at that instant just after the string between A and B is cut is same as the initial elongation of spring before the string was cut. So magnitude of elastic force by the spring on block A at the instant just after the string between A and B is cut will be again equal to 3 mg. So resultant force on block A in the upward direction will be equal to magnitude of the upward force minus magnitude of the downward force. That is equal to mass of the block A and magnitude of acceleration of the block A. Magnitude of elastic force by spring of the block A at the instant just after string between A and B is cut is 3 mg. Because the spring will have the same elongation which it had just before the string was cut. At the instant immediately after, the elongation of spring just after the string between A and B is cut can be taken to be same as elongation of spring just before the string between A and B is cut. So mass of A is 2m. So you can simplify this. You get magnitude of acceleration of the mass A equal to g by 2. And this acceleration will be directed upwards because magnitude of elastic force by spring is 3 mg, which is more than the weight of the block A. So net force on block A directed upwards. But after the string between the two blocks A and B is cut, no tensional force acts on the block B. So the block B will be moving only under influence of gravity. That is only external force acting on the block B. Just after the string between A and B is cut will be equal to its own weight. Therefore, it falls with an acceleration equal to the acceleration due to gravity. So net force of block B is equal to its weight. That is equal to mass of the block B and magnitude of its acceleration. So magnitude of acceleration of B will be equal to g. This will be directed vertically downwards. Those who want to copy the solution of the problem, they can take a pause and copy the solution of this problem. So for the question number 43, second option is answer. See the question number 44. A and B are two nails on a horizontal line. AC, BC are two uniform light strings from weight of 100 Newton is suspended. The magnitude of tension string AC is in Newton. So there are three tensional forces acting at this point C here. Let T1 denote the magnitude of the tension in the string AC. Let T1 denote the magnitude of tension in the string AC that acts along the string and away from C. Let T2 denote the magnitude of tension in the string CB. So the tension force exerted by the second string connected between the point C and B on the particle at C acts along the string and away from C. There will be third tensile force on C. Exerted by the vertical string. The third tensile force exerted by the vertical string and the particle at C acts along the string and away from this particle at C. If you draw a separate free body diagram for the block, two forces act on the block. One is its weight mg, which has a magnitude of 100 newtons, and tension force by the string on the block acts upwards, which has a magnitude T3. So magnitude of tension at the lower end of the third string will be same as the magnitude of tension at the upper end of the third string. So resultant force of the block is equal to T3 minus mg. Because the block is in equilibrium, this must be 0. So magnitude of tension in the third string, that is the vertical string, is same as the magnitude of weight of the block, which is equal to 100 newtons. Now let us suppose this angle is equal to theta. So we have ACB, the right angle triangle. So angle at C is 90 degrees. So the angle at B will be 90 degrees minus theta. From Pythagoras theorem, length of side is AB. Length of the side AB is equal to under root of AC square plus CB square. AC equal to 3 centimeters, BCB equal to 4 centimeters. So length of the line AB is 5 centimeters. So from this figure, you can observe that sine theta equal to length of side opposite theta divided by length of the hypotenuse, that is BC by AB. So 4 centimeter by 5 centimeter. So you get sine theta equal to 4 by 5. From that you get the value of cos theta also equal to 3 by 5. Now you can apply Lami's theorem for the force acting at the point C. The angle between the two tensile for T1 and T2 is 90 degrees. What's the angle between T1 and T3? Draw a horizontal line through the point C parallel to AB. This T1 makes an angle theta with the horizontal direction, whereas T2 makes an angle 90 minus theta with the horizontal direction. Therefore, angle between T1 and T3 at the point C. You can draw separate figure showing the forces acting at the particle on the particle at C. So T3 acts vertically downwards. So T1 acts on the particle at C. At an angle theta above the horizontal, that means this angle will be 90 degrees plus theta. And T2 acts perpendicular to T1 at the point C. The angle between T2 and T3 will be 90 plus 91 of theta. So 90 plus 91 of theta will be 180 degrees minus theta. Can apply the Lami's theorem, which is based on sine rule. When the three coplanar forces acting at a point are in equilibrium, then the magnitude of each force is proportional to the sine of the angle between the other two forces. So from Lami's theorem, you can write T1 by sine of the angle opposite T1 is 181 of theta. Equal to T2 divided by sine of the angle opposite T2 is sine of the angle between other two forces opposite T2, 90 plus theta. T3 by sine 90 degrees. So combine first and last. So T1 by sine 181 of theta is sine theta. Right side T3 is 100 newtons. Sine 90 degrees is 1. So T1 is equal to 100 Newton into sine theta. Sine theta we got here 4 by 5. So you get T1 equal to 80 Newtons. So magnitude of the tension in the string AC is 80 Newtons. I have actually solved a similar problem in the past by another method, by component method. That means you can consider the free body diagram for the forces acting at the point C, and you can resolve the tension forces T1 and T2 in rectangular components along the horizontal and vertical directions. So the other method already I have discussed in one of the problems in the past. That's why I'm not repeating that now. So those who want to copy the solution of the problem, they can copy the solution of the problem.